Hi, today we will talk about single-phase induction motor. So until now, we talk about the three-phase induction machines. Actually, we don't have three-phase plugs in our homes or home appliances. So how does induction machines work with single-phase supply? So before getting into the single-phase supply, one of the main idea of three-phase induction motors are the rotating MMF concepts, and actually it is the same for all three-phase AC machines. So the idea is like, yes, we have like pulsating waves or pulsating MMS created by like one of the phases, and we have like other vectors here, and when you combine all those things, when you combine these three separate pulsating waves, you get a traveling wave with a constant magnitude. So its magnitude is 1.5 here. So that was the idea of three-phase supplies, and why we put them 120 degrees apart between each other physically, and why we have a time difference between them. So the problem is, if we have just one phase, so here you see the phase A, yes, it will create some MMF, but that will be a pulsating wave. So the direction of that vector will not be changing. So actually, if you just put a permanent magnet or salient pole rotor, so it will not move, but it will just try to fix in that MMF direction. So the question is how we can obtain a rotating MMF with that kind of a pulsating wave. So actually, if you mathematically express a pulsating wave, what you will see is it has some magnitude, okay, of f max, let's say in this case, and it has a time function, and in that time function, actually it is it's the things that make things pulsating. And the other component is, in this one, is the rotation or the x component. So it gives its shapes. Okay, so actually there are two cosines. One of them is changing its magnitude with respect to time, and the other one is multiplied with that one is another cosine distribution with respect to the coil distribution. And one of them is called the time dependent component, and the other one is called the position dependent. And actually that is again that is what we have for the three-phase waveform. So you can see how it creates rotating, and there's really a nice mathematical trick going on here. So I want you to have a look at in that animation. So what we have here is two actually the red one, okay, so red one is the MMF created by a single phase AC winding, or it can be expressed like that. That one here, it is the red one. So if you just look at the red line, so you will see it is a pulsating wave, it has a time component, and it has also some position component. And actually the blue and green ones are the two components, or let me rephrase it like that. If you add the blue and the red sinusoids, you will have the red one. Okay, so when they are in phase, when the blue and green phasors or sinusoids are in phase, they will have the maximum magnitude, and when they are 180 degrees apart, actually they cancel each other, and that is the moment where you have zero magnitude. So that is really important phenomenon. So it says a pulsating MMF can be separated into two components. One of them is the forward rotating, and the other one is reverse rotating. So suddenly in the previous cases we need three pulsating waves to create one rotating MMF, but actually if you have a look at the pulsating MMF, actually it consists of two opposite rotating traveling waves. So actually it is called double rotating field theory. Maybe you have heard it before in the waves or in physics. So I would like to show a couple of videos to demonstrate that one. So the idea is a pulsating wave is addition of two waves moving in the opposite directions. Okay, so here we have a wave tank. So actually they have a moving device, so it can create some waves. Okay, so let me play that video, and here if you look closely it will start sending some waves, and once they are coming in that direction, you can clearly see they are kind of moving, right? So you have the traveling wave already, and then you have a wall here, so they will hit the wall and they will travel in the opposite direction. So what you will see is the effect of two opposite waves traveling in different directions. So now they are coming out here, they are hitting the wall, and they will start going backwards. And once they make that rotation, now look at the waves. At first they were traveling, but now it is not traveling, but became a pulsating wave. Why? Because you have one wave going in the forward direction is created by that motion, and the other wave is traveling in the opposite direction. So once you combine these two, actually they look like it's pulsating, but actually a pulsating wave consists of two opposite direction waves. And actually there's another video on acoustic levitation, how you can lift objects using sound waves. So they actually use the same idea, but I don't want to waste some time, and I suggest you to watch that video as well. So a pulsating wave, actually mathematically, if you just express that one, so that is what was happening in the pool, in the waves. So the waves are hitting the wall, going in the opposite direction, so you were seeing the pulsating red one. So actually you can represent that one using those two components. I don't want to get into the mathematics of it in this video, but actually you can do the tricks and you can write the cosine terms, and you will see once you make the trigonometric equations, you will have the cosine omega t out of the equation, then you will have the cosine theta e components. Okay, so the first one is called the forward rotating component, and the second one is the reverse rotating component. So what does these things have to do with the single phase induction motor? So the idea is, okay, in the single phase induction motors, if somehow I can generate a pulsating wave, right, so which can be obtained by two phasors, that can mean maybe I can create some torque using that reverse revolving phasors. So actually here you see a nice animation in the phasor domain. Everything the same that we have seen in real time can be represented in phasor domain. So if I have like two opposite direction rotating MMFs, which corresponds to two phasors with equal magnitudes rotating in different directions, so you have the forward rotating and reverse rotating components, and actually if you add them in the phasor domain in the vectoral form, so you will have that kind of pistons moving up and down. So actually the black one is the MMF created by our phasors, and actually you can see this thing is equal to a pulsating wave equal to two phasors rotating in opposite directions. Okay, it is not only in this course, so there are like many different applications for this phenomenon. So it's really important to understand it's both in the physical form, both in phasor form, and both mathematically. Okay, so we have like torque, like conventional three-phase induction machines has torque characteristics like that, so they cannot generate any torque at the synchronous speeds. So they have a starting torque or stall torque, and they create some maximum torque at some slip, but usually they are operated around this region. So what will happen if we have two different rotating phasors. So if you think about it, the torque in a single phase machine, if you are, for example, going in that direction, if the rotor is already rotating in that direction, so for the forward component, okay, for the forward rotating component, you will be working in the motoring region, so it will be producing some torque. But for the reverse rotating component, actually, according to that one, because what you were saying, like, one train is, let's go to that concept. So one train is going at 90 kilometers per hour. So that is our MMF, rotating in forward direction, and our rotor is rotating, moving at, let's say it's a train, so 80 kilometers per hour. So if you look at from rotor to the 90 kilometer per hour train, so you will see that is going forward, at 10 kilometers per hour. So you have a small slip, so you are working at that direction. But what we said, so there are actually two phasors rotating in opposite directions. And for other train, so your rotor is going at 80 kilometers per hour, but the other train is going 90 kilometers per hour in the opposite direction. So the resultant speed difference is 170 kilometers per hour. So actually your slip is larger than 1. So for the other, backward rotating version, so you were like that, you were working in that direction. So it is, technically like in the, braking region. One of them is trying to increase the torque, and the other one is working as a generator or plugging and try to slow down the motor. And actually, once you add these two curves, okay, once you add these two curves, what you will see is, yes, they will be identical and they will cancel each other, so you will not have any torque still at the synchronous speed. But when the rotor is stopping, okay, one of the train, so you are stationary, one of the train is going at 90 kilometers per hour in that direction, the other one is going in the opposite direction at 90 kilometers per hour. So the torque components they generate will be equal, but in the opposite directions. So when you add the torque generated by the forward rotating component and the reverse rotating component, actually they cancel each other, and you will get a zero torque at stationary. So that is really important for single phase induction motors. Technically, if you just get an induction motor, three-phase induction motor, and if you excite it with by single coil, it will not self-start. But somehow if you just make it rotate slightly, or somehow if you generate some initial torque, then it can start rotating. It will not be like as efficient as a three-phase induction motor, because there is always some negative torque component, so they will try to slow down the machine. But at the end, you can create some net torque. And actually, you can click on that link, and you can find a spreadsheet to estimate the torque of a single-phase induction machine, and you can play with parameters to obtain that kind of characteristics. So our next problem is, okay, I can have with single phase, I have two rotating phasors, but it cannot self-start. But what if I have two phases? Okay, so I don't have three phase. What if I have two phase apart from each other with 90 degrees? Okay, so here you see one sine and another cosine. So if I have two phasors like 90 degrees apart from each other, and if I excite those things, can I get a MMF similar to that one? So here you see we can generate a rotating MMF with three phase, but can I do the same thing with a two-phase configuration? So technically, yes. Here on the top you see a three-phase configuration, which the the phasors are added and you have that configuration. And in the bottom you see a two-phase configuration, which you have the orange and the purple ones. And actually, again, if you look at the orange one, it is just going up and down, and the purple one is horizontal. Its direction is not changing, but they are 90 degrees apart from each other, so they can create a rotating MMF. Okay, so with single phase, purely single phase, technically yes, we can rotate, we can create rotating phasors, but the torque components will cancel each other. So let's have a look at what will happen with two-phase configuration. But the problem is, yes, okay, two-phase winding can create rotating MMF, but how can you imitate two-phase excitation? And at your house plugs you have just line and neutral, so it is just one phase. So how we can do that? So actually there are like different configurations. I will show you the details in a minute. The idea is, if you have a coil, okay, which has less number of turns, for example, so it will have a low inductance, okay, so it will have some power factor, there will be some phasor with the current. Then to the same voltage source, if you connect a second coil with higher number of turns, for the second coil it will be more inductive. Okay, so I'm talking about the ratio between L and R. So at the end of the day, it has an impedance. That impedance will have an angle. So depending on that angle, actually the current phasor or power factor can be modified. So if I have two coils with less number of turns and with higher number of turns, or with a more resistive, less inductive and more inductive coils, there will be some phase difference between those things. Maybe it will not be perfectly 90 degrees apart, but I can adjust the number of turns to create some artificial phase winding. So let's have a look at how does it work. So I can have like split phase motors, try to use two orthogonal like windings. So the idea is to have, you know, that kind of 90 degrees. So in the ideal two-phase configuration you want to have like 90 degrees apart, but if it is not 90 degrees but 80 degrees, that will work okay as well. So let's have a look at that one. So first we will have a main winding. These are called main winding. Another one is called the auxiliary winding or the starting winding, and the auxiliary winding have higher resistance to reactance ratio. Okay, you use a thinner wire, so by changing the wire thickness and actually the number of turns, so you can adjust the impedance angle of those wires. So how does it work? So here we have an animation. So first I would like to show you the ideal case. Okay, so in the ideal case they have the equal magnitudes, phase A and B, and they are 90 degrees apart from each other. Okay, again, once you do that, here on the left hand side you have the phasor of one winding, the other one is the phasor of another winding, and the net winding, if you look closely, so it is rotating and its magnitude is constant. Okay, its magnitude is constant at 1, so you will have those two, and actually you can see those pulsating waves can be separated into forward and reverse rotating components. Again, it is outside the scope of discourse, but backward components cancel each other. They are 180 degrees always, and the forward components are in phase, so the forward components are added together to create the same thing. So the left hand figure and right hand figure, they are showing the same thing, but the right hand one also shows the forward and backward rotating components. So instead of just defining 90 degrees between each other, let's change the angle. Okay, so let's reduce that one to 67.5 degrees. So here, it's like a orbit of a planet. Okay, So it's not ideally circular, but it's like an elliptic orbit. Okay, its magnitude is going up, it's going down, it's getting maximum, but at the end of the day it is still creating some rotating MMF. So if you just put some permanent magnet rotor, it will try to rotate that one, but the torque will not be constant. There will be some torque ripples, that kind of vibrations. That is why single phase induction machines are much more noisy than their three phase equivalent size motors. So actually, if you have a look at those ones, now the backward components are not totally out of phase, so they don't cancel each other, and again forward components are not ideally aligned, so there is a angle difference between those ones. So let's, I don't know, decrease the angle 45 degrees. So even at 45 degrees, so you have some kind of rotating MMF, but it gets worse. Okay, so 90, let's make it slightly larger. Okay, and actually you can still, they don't have to have equal magnitudes. Let's do that one, and let's make 90 degrees, and let's decrease the magnitude of B. Okay, so phase A draws more power than phase B, so you can see that in the phasor directions here, and again it gets into an elliptic shape, but you can still create a rotating MMF. So how we can do that that effect? So actually we have a single phase, supply. Okay, so I have the main winding as here, let's say phase A in the previous animation. So you have some number of turns here, and then I put the auxiliary winding. Okay, auxiliary winding has different number of turns. Usually that's used for thinner wire. So I can add that one. So I can simulate the motor. Because the phase of the current drawn here will be different from the phase of the current of that coil. They will not be like 90 degrees apart as in an ideal case, but actually there will be some phase difference, and even if it is an elliptical orbit kind of rotating MMF, it will create a net torque. Okay, and once the machine starts rotating, what can I do is I can turn off that switch. I can eliminate that auxiliary winding or the starting winding. Okay, then once the machine just start rotating, then I can switch to single phase configuration, because I know in the single phase configuration again there's some forward and backward direction MMF, so I can run the machine. So the addition of that extra winding, is to just eliminate, because if you just use a single phase winding, the forward and reverse rotating components cancel each other, so you don't get any starting torque, so the motor cannot self-start. So I can simulate a two-phase configuration, but once the motor gets running, I can eliminate the motor and I can continue running as a single phase motor. Okay, so with the main winding only, so you will have no starting torque and you will have that kind of configuration. But with main and auxiliary winding, you will have a starting torque, then it will come down to here. Yes, technically you can keep running the motor with both of the windings, but because of that one has a thinner wire and more resistance, actually that affects the efficiency of the motor in a negative way. It reduces its efficiency. So we just started with main and auxiliary winding, and once it reached some speed, actually I can turn off that winding, and I can run as well as a single phase winding. So the problem is how I can make that kind of switching and disconnecting the auxiliary winding. So actually there are some kind of centrifugal switch. So here you see an example. So they are really nothing but, so as you see a spring, So there is a mechanical mechanism here. So once it reaches some, predefined speed, the centrifugal force becomes enough to get over that spring force, and it just disconnects the auxiliary winding. Okay, so it's usually like 75% of the rated speed. And actually in this video again you can find some electronic alternatives, because the mechanical switches can have some reliability problems. So in modern single phase machines you can also find electronic centrifugal switches. So instead of having two different number of turns, windings, they are called the split phase induction machines or split phase motors. There are other alternatives. So because split phase motors has some moderate starting torque, and the advantage is they have low starting current, but because of that one, they can have problems with loads that require high starting torques. They are used in fans, pumps, office equipments, etc. The other one is the capacitor start type motors, and actually I think this is the most common single phase induction machine type. So the phase displacement is created by a series capacitor, because if you have an inductance like that and a capacitor like that, and once you close that switch, the current drawn here and the current in that direction will have different phasors. So you add a capacitor to that position. And again, with the capacitor switch, you can have like the main winding, and you will have some phase angles between the auxiliary winding as well. And because of that difference, you can manage to create initial starting torque. And the idea is same. Once they have some enough speed, you can turn off that switch and the machine can run purely as a single phase induction machine. So again, as you can see, the starting torque of capacitor type motors are much larger, because you can manage with the help of capacitor, you can manage to increase the difference, current difference between those two branches. Okay, so they have high starting torque, and because of that one, they are used in compressors, refrigerators. Probably in your homes, in the refrigerator compressor, you have that kind of motors. And actually you can here you see a proper example. You can understand a single phase induction motor with that cylindrical addition next to their frame, and inside of that casing you will find a capacitor to create the phase difference between auxiliary windings. And here there's a pump, I think. Again, you see a capacitor casing for single phase induction motors. And actually there are not always you have a switch, depending on the application and design of the machine. You can have a permanent split capacitor motor, so they don't have a switch, they run with the auxiliary winding. So you have single phase supply, and by addition of that capacitor you can create two-phase configuration, and the machine can run as a two-phase machine. Okay, and again there are like other machines which can create high starting torque, but once it reaches some speed you can add or remove extra capacitors to adjust for the efficiency or torque characteristics as well. So again, I don't want to get into the details of the equivalent circuit, but the equivalent circuit of a three-phase machine, because that corresponds to rotating MMF concepts. But now we have two rotating MMFs, so I can divide the equivalent circuit into two components, one for the forward rotating component and the other one is for the backward rotating component. And here you see a typical equivalent circuit at standstill when the rotor is stationary. So again, you can have the main winding, and you have the same components, same currents getting into the first series branches, so they can be combined. But later on you have the forward rotating MMF, or induced voltage, and the rotor side equivalents of the forward rotating components, etc. And since they are divided into two, that's why we have 0.5 exclude 0.5 R2. Normally, remember, it is R2, and we have, we can divide those components as R2 and 1 minus S over S R2. We have the same thing, but since it is a standstill, they are equal, so the torque created by that one and that one will cancel each other ideally. But while running, what we have is, normally we have, yes, it is R2 prime over S, which is, R2 prime and 1 minus S over S R2 prime. So that one is identical, same with a single, with a three-phase induction machine, no problem there, R2 prime over S. But the other one is actually R2 prime divided by 2 minus S. Okay, 2 minus S. What does it mean? So it means, let me go back. So here again, if one of the forward rotating components is in the motoring range, or the reverse rotating component, actually you are in the plugging mode. Okay, so that one is actually trying to stop the motor. So rotor, from the backward component's point of view, is trying to rotate into the counterclockwise direction, but the rotor itself is rotating in the opposite direction. So it is not the motoring mode, it is the plugging mode. And actually we see, that thing, or we can estimate the generated torque using that equivalent circuit. So according to that one, it is not S, it is 2 minus S. Okay, for example, for 90 kilometers per hour, we had 80 kilometers per hour. So slip is, let's say, 10 kilometers per hour for the other one. But depending on the train that is going in the opposite direction, it's going 90 kilometers per hour. The other one is going 80 kilometers per hour. So the speed difference is 170 kilometers per hour. Or in other words, 2 times 90 kilometers per hour minus 10 kilometers per hour, 170 kilometers. Okay, so again, I don't want to get the numerical calculations in this video, but the important thing is, okay, so the forward component works in the motoring mode, but backward component actually works in the plugging mode. It actually tries to stop the motor. So you are still giving some electrical energy, but that electrical energy for the backward component is not converted into mechanical energy, and moreover, actually it steals some of the torque generated by the forward component, forward rotating component. So, that is why, single phase induction machines can be useful, can operable if you have an application where, for example, the efficiency is not that critical, but the cost is critical. Then it makes sense to use single phase induction machines. But in the recent years, efficiency becomes a really important factor. So that is why, for example, for air condition systems, for washing machines, for refrigerator systems, they say inverter driven AC, inverter driven washing machine, inverter driven refrigerator. And the idea is, instead of using conventional single phase supply and using single phase induction motors, which has a low efficiency due to that fact, having two opposite components, modern efficient appliances actually uses a three-phase motor. It can be a permanent magnet induction motor, but at the end of the day, it's a three-phase motor. And between the single-phase supply, where we have the neutral and line, they have some power electronics devices. They have inverters, variable frequency motor drives. So they convert AC to DC first, and they convert that DC to three-phase AC at whatever voltage or frequency they require. So in the overall, you get a very efficient motor and nice torque without ripples, so they can eliminate some acoustic noise. It can be operated really silently. Anyway, that power electronics and all those motor drives are the topic of our next year courses. Okay, that's all. Thank you.